Right. For chapter 13, you need to review the energy, which was from chapter 7. And chapter 13 begins with entropy. And so we're going to look at entropy in two ways. One way is qualitative, the other way is quantitative. And so I talked about how do we calculate entropy. And then there are two ways that we could calculate the entropy. One is by counting the microstates. But for chemical systems, with so many microstates, we need to use statistics to generate these. You could do it for simple systems like this. There may be a homework problem with that. And the Boltzmann equation here, where we can count the number of microstates, W, or the number of ways that the microstates can be arranged. And Kb is just the Boltzmann constant. The Boltzmann constant is given here in terms of joules per Kelvin, 1.3807. We'll also need to know R, 8.3145 joules per mole Kelvin, and Avogadro's number 6.022. Usually I do Avogadro's at 468. We could do it for 568 here. 6.0221. And our Boltzmann constant comes out to 1.847 times 10 minus 23rd joules per Kelvin here. Okay. And so we can see the number of ways are going to increase tremendously, even for very simple systems. So in this expression, the power of 10 is a 1 followed by 23 zeros. The value of W is a 1 followed by 10 to the 23 zeros. When you write down these digits on a piece of paper at a rate of 1 million digits every second, it would take 10 to 17 seconds or 3 billion years to complete. So it's the number of states, microstates, is enormous. Okay. Now, entropy. We'll look at qualitatively first. And which one has higher entropy? If you constrain the gases on the left or allow the gases to go through both containers, which one would have higher entropy? The second one. This one has higher entropy because there are more microstates. This is called positional entropy. Positional entropy is, what position these are. Now, if atoms are vibrating, what position are the atoms in vibrations? That kind of stuff. So as far as positional entropy goes, this one has, twice the entropy because it's got twice the volume. Do you see that? And so entropy is an extensive property like energy. If you burn twice as much methane, you're going to have twice as much heat, basically. And so entropy is the same kind of deal. If you have twice as much, you're going to have twice as much entropy. And so it's extensive in that sense. What about energy? Which one has higher energy? How can you tell the first one has higher energy? Let me tell you what we're going to do here. In this case, what we're going to do is we're going to start off at 25 degrees C, and we're going to end at 25 degrees C. Even though when gases typically expand, have you ever noticed this? Like if you have one of those keyboard cleaners of compressed gas, what happens to the can? It gets cold. So normally when gases expand, energy, because it's like blowing up the balloon. So essentially the system blows up the balloon, it doubles in volume. Well, in order for the system to double in volume, it had to do work. And therefore, where is it getting the energy for the work? It's getting the energy for the work from the surroundings, like your hand. Your hand is warming up the can to give it the energy to do the work to expand the volume. But what we'll do is this. Okay, initially when it expands, it does work. And then it's going to take energy, but we'll just wait until it goes back to room temperature. So if we wait until it goes back to room temperature, which it will, then if we start at 25 and we end at 25, what was the change in energy? Zero. Because this is only kinetic energy. These have got blue dots there. We don't know what the chemical potential energy of that is. This is some ideal gas. And so here, this reaction, actually it's not really a reaction, but this process is driven by an increase in positional entropy. And so the driving force for this, and we expect this, when we open this, we expect it to expand out and fill both containers, correct? Mm-hmm. And therefore, this is driven by entropy alone. And so how do we quantitate, what is that driving force in terms of entropy? Well, the first thing we got to do is we got to figure out what is the entropy change in something like this. Or something like this, whatever our initial entropy was, it's doubled now because we have twice as much. So first off, we'll just look at it qualitatively. Here's another scenario here. Obviously, we're going to get the red ones expand and the blue ones expand here. And so this is entropy driven too, because we could start off at 25, end at 25. Nothing's changed. It's not going to stay cold forever, right? In the room. And so it's entropy driven. So first off, okay, yeah, we see the entropy increase, but how much did the entropy increase by? So these are two questions that we're interested in. And so, let's see, expansion of a gas into a vacuum is not only spontaneous, but also instantaneous. It's generally true that a spontaneous process is also instantaneous. Explained, well, spontaneous means there's a driving force. But sometimes it's not so instantaneous. Sometimes it takes time. And so this concept assessment sometimes is a little barrier to spontaneity. This is what this is looking at is this is like counting the microstates. So this is one way we could do it is we could count the microstates. But would you want to count the microstates in something like this, even though it doesn't have that many particles? I mean, this would be ridiculous. This is because there's a lot of empty space there, and the position of this could be anywhere in there. And so, how many things are you going to count there? This is huge. This is why we need things like statistical. But then, there's certain things that can simplify this. When we look at this is a one-dimensional crystal. One-dimensional crystal that consists of 4 molecules. Then you can count the number of microstates. Okay, we count the number of microstates in a 4-molecule nanocrystal, something like this, and we can figure it out. Okay, we can relate it to changes in volume. Of course, increasing volume is going to increase the number of microstates that are possible. And so we can see things like this, which I'm going to skip. So, for example, let's take a look. How many microstates are there for 4 neon atoms confined to a 905 picometer box? The total energy. So here is the total energy of this. And total energy is going to determine, the population of the microstates here. If I have microstates like this that can be occupied, then most of them are going to be at the lower energies. We have something that's going to look like this as far as population goes. Depending on the energy. What this is the familiar Maxwell-Boltzmann distribution curve. Flip on its side. And so the greatest population, this is population versus energy. Yeah. The population, if the energy increases, the average kinetic energy or average energy increases, or whatever energy we're looking at increases, then the population is going to shift. The same thing here. At lower energies, the population is down here. At higher energies, the population shifts up. So we can see it based on the population of the dots here sometimes. There that goes. But again, probably in the homework we'll look at one of these and then just see. Okay, so this is qualitative, and we looked at some of the data yesterday. Pure liquids or liquid solutions increase in entropy. Well, Well, you know that solids have entropies from 0 to about 100, liquids are about 100 to 200. So if we're going from solid to liquid, that's going to be about a delta S of around 100 joules per Kelvin. The units for entropy will be joules per Kelvin mole. If we're going from liquid to a gas, liquids are about 100 to 200, about 300, so it's about another plus 100 not kilojoules, joules per Kelvin. Here we're taking a solute and a solvent. Here, this is a bit more tricky because what is the entropy change here when we're forming a solution? Now, this brings up one of the things that we have to remember, and that is this. The reason why absolute internal energy and absolute enthalpies are not determined. These are typically not determined, or if they are determined, they're determined with a significant error associated with it. And the reason for that is because what is the absolute zero of energy? Can you tell me what the absolute zero? I can tell you what the absolute zero of temperature is. It's 0 Kelvin. But at 0 Kelvin, are the electrons frozen or are the electrons still in motion? The electrons actually never stop, even at 0 Kelvin. The atomic motion stops, the molecular motion stops, but electrons don't stop. They don't freeze. That's called the 0 point energy. But what is the absolute zero of energy? So if you take a water molecule, what is the absolute? Oh, you freeze that water molecule down to 0 Kelvin, but that's 0 kinetic energy. What's the absolute zero potential energy for that water molecule? Well, anyway, that's, there's potential energy stored in the bonds. Well, not even in the bond, there's potential energy stored in the hydrogen bonds holding the water molecules together in an ice crystal. There's potential energy in the bonds. There's potential energy in the electrons being held to the nucleus. There's potential energy in the nucleus being held together. Okay, so how much can you break the nucleus down? Because, there's protons and neutrons. They're held together by nuclear binding forces. And so you break apart the protons and neutrons. Can you break down the protons? Can you break down the neutrons more, or is that it? Well, actually, you can break them down further into quarks and whatever else. So maybe the particle physicists haven't figured it out. They can get it. And I think they're talking and they have it pretty well sorted. But it still doesn't give accurate calculations, unfortunately. So we don't. But absolute entropy, we know the absolute zero of entropy. What is the absolute zero of entropy? It's given by a law of thermodynamics. The absolute zero of entropy is it's zero. Actually, the absolute zero of entropy is zero, right? You can't get any lower than zero, and that's for a perfect crystal at 0 Kelvin. So how are we getting negative entropy? It's like, what is the absolute zero temperature? The absolute zero temperature is 0 Kelvin, right? But how are we getting negative temperatures? What's the meaning of a negative temperature? Does negative temperature mean that all of a sudden we're in some inverse universe, or everything's moving backwards? We can't have negative Kelvin, but we can have negative temperature, right?
Those are just different scales.
Yeah, different scales.
Scale would go down to negative, what is it, 100?
Negative 273, 115. Yeah, Fahrenheit would go down to negative 400, something.
So you can't go below those. Those are like the absolute zero.
Yeah, but what does the negative mean? It's not a reversal of anything. It's not like one's emitting, one's absorbing, or that kind of stuff. It just means it's colder than some arbitrary 0 point that somebody made. What was the arbitrary 0 for Celsius? The freezing point of water. What was the arbitrary 0 picked for Fahrenheit? Well, 0 Fahrenheit means what? It's below freezing, but what did it, well, who decided what 0 Fahrenheit is and why is 0 Fahrenheit 0 Fahrenheit? 0 Fahrenheit is below freezing of water. For water freezes at 32, so there must be something significant. Was it that Fahrenheit went outside and it was super cold and he said, this is probably the coldest I've ever felt in my life. I'm going to call this 0 Fahrenheit because I don't think temperature can get any colder than this. Yeah, maybe so. We have no idea. Actually, we have an idea. Do you know what 0 Fahrenheit is referenced to? The freezing of a salt solution. You know, like if you make ice cream or something, you put lots of salt water, you get temperatures, cold temperatures. Well, this is saturated salt solution or brine solution that froze at that particular temperature. So it's reproducible. So it's not something totally arbitrary. And so it turns out that you guys are supposed to know this for thermodynamic tables. You're supposed to know that there are two scales in thermodynamic tables. But they don't call them different units. They call them the same units. So that's probably why a lot of people get confused with this type of stuff. So this is the last point of review from chapter 7. Last thing I want to review from chapter 7 is that there are actually three tables inside this one table. It's like there are three temperature scales, right? Fahrenheit, Kelvin, Celsius. Well, there are three tables inside this one table. When we look at delta H. And so what are the three tables? Let's go to B, C, D, past it. There. We have a table for the elements and the compounds. So we can compare elements and compounds with one another. And that's going to be our delta H. Then we have a table for cations. So we can compare cations with other cations. But we don't compare cations with elements and compounds because it's meaningless comparison. It's like saying, okay, you know, what's a hotter temperature, 100 Celsius or 101 Kelvin? You know, but a lot of people, they don't have the units there. So what's a hotter temperature, 100 or 101? Well, automatically you say 101, and then I throw it out. Well, 101 Celsius or 100 Kelvin? And all of a sudden it switches things, right? Well, it's the same thing here, but the problem is everything's kilojoules per mole. But, you know, you're supposed to be sophisticated enough to know that there are three tables here. And you have to keep track of that, right? And so what it means is that the cations are referenced. Well, what is a cation reference to? Well, this is picked as an arbitrary 0 for cation. So this would be like 0 Fahrenheit. You know, who picked it? I don't know who picked it, but somebody picked H plus to be 0. And so anything that has a delta H of formation, you know, that's greater than or less than will be always referenced to this as far as cations go. You know. And then what's the anion 0? Well, there's no anion 0 actually. The anions are referenced like this. So if I'm looking at the delta H formation of HCl, and you guys remember what this symbol means? That's superscript 0. What does that superscript 0 mean? This is going to come into importance here. Not STP. It doesn't mean STP. The superscript 0, which we see here, means what? Okay, I'll tell you, you know, like I said before, this is the reason why people fail miserably at thermodynamics, because they don't know what these things mean, or You know, and if you don't know what it means, and then all of a sudden things get a lot harder, you know, you're always on a shaky foot. That was me. You know, I didn't know what that. I didn't really, because you know my instructor didn't really um, go into it. You know, and then you know my first quarter at UCLA it was a struggle because I was taking thermodynamics and I had no idea. I didn't really care. You know, what is that little superscript? Well, it doesn't really matter. Just some thing, but it's very important because if you don't have that, it means you have to use totally different calculation. That means standard thermodynamic conditions. Standard thermodynamic conditions is not STP. There's no standard temperature. There's no standard temperature, but there's a common temperature because most people work at what temperature? Most people work at room temperature. Room temperature has been decided by somebody to be 25 degrees C, 298 Kelvin. That's room temperature. But it's not standard because anybody can work at any temperature they want. So let's say the room is a little colder. Well, we should be able to work at that temperature. But this data table, we can't have a huge number of data tables for a huge number of temperatures. So this data table is just picked for 25 degrees C. But standard thermodynamic conditions is defined in the table here. And so the footnotes are very important to read on tables like this because the footnotes often give you crucial information. And so let's see where the footnote is here. Well, the footnote is actually in the heading here. Thermodynamic properties of substances is 298.15 Kelvin. That's not standard temperature, but that's the most common temperature. And then substances are at 1 bar pressure. That's standard. It used to be 1 atmosphere, but this is 1 bar. For aqueous solutions, solutes are unit activity, roughly 1 molar. Data for ions in aqueous solutions are relative to values of 0 for delta H of formation for H+. So H+ is chosen as the arbitrary 0 for everything, for the ions. And so what this means is standard. This little standard means we have to be at 1 bar and 1 molar concentration. So 1 bar gas pressure is 1 molar ion concentration. And so this is at 1 molar. If we have 2 molar, then that's going to change things. In terms of delta H, it's going to double things, perhaps. It depends. And so the delta H information, this comes about because we can't separate this. If we do calorimetry, we want to do delta H information to HCl. Delta H information of HCl is going to be the delta H for this reaction. It's going to be 1/2 H2 gas plus 1/2 Cl2 gas is going to yield HCl aqueous here. When we form HCl aqueous consists of H plus Cl minus. And when we do the delta H of this reaction, the delta H of this reaction comes out to minus 167 kilojoules per mole of HCl formed. Now, minus 167 kilojoules, how much of that comes from forming H plus, and how much of that comes from forming chloride? You know, is it 50-50, 50% H plus, 50% chloride? Well, we could try to use calculations, you know, quantum mechanical calculations, but those are going to be a little bit of error. And so rather than having something that's going to have error, they just attributed it to this. This is going to equal the delta H of formation of H plus the delta H of formation for Cl minus. Yeah. And since we can't tell accurately, super accurately, which one, exactly how much comes from H plus and how much comes from chloride, well, then it's arbitrarily defined. The arbitrary definition is, by definition, this somebody selected this as 0 kilojoules per mole and then made it all chloride. Is that accurate? No, that's not accurate. You know, so chloride is going to be minus 167 kilojoules per mole here. And so when we look at chloride, we see it's a minus 167. kilojoules per mole. And H plus is 0. So that's it. So there are 3 tables here, that we look at. And that is, again, one for the cations, one for the anions, one for everything else. And so that's why we get negative numbers. We see lots of negative numbers in the entropy. That's why we have negative numbers in the entropy here, because let's take a look at the entropy of H plus. If we look at the entropy of H plus, could it be possible that H plus, 1 molar H plus aqueous has an entropy of 0? That's impossible. But how is it so? How is it so is because if we're looking at the entropy of this, the change in entropy here is going to be delta H is the change in entropy, but delta S would be the change in entropy. The change in entropy would be the entropy of the products, HCl, minus entropy of the reactants. Here. When we look at the entropy of the products, how much of the entropy is from the H plus and how much of the entropy is from chloride? Well, we can kind of guesstimate using calculations, but we aren't. What we're going to do is we're just going to set one of these to have an entropy of 0, and all the entropy goes into chloride. And so chloride's going to have let's see what the chloride entropy is. Look at the chloride's entropy. Minus 136.4. That's bizarre, isn't that? But that's because of the way we do things with the arbitrary 0. So actually, we'll do some calculations. The calculations are quite easy. Actually, we can figure out what the entropy change is for this. Let's go ahead and figure out what the entropy change is for this. So delta S, we are not going to use KB, the Boltzmann constant, ln of W. That would be way too much work. So we're going to have half a mole, and a full mole. So delta S is going to be the sum of the entropies of the products minus the sum of the entropies of the reactants. We have to change, since entropy depends on how much we have, we have to do the same thing we do for delta H calculation. So we have 1 mole of HCl. 1 mole of HCl aqueous, do we have that here? So let's see, HCl. Okay, 1 mole of HCl aqueous has an entropy of minus 136.4, which is kind of bizarre to think about because absolute 0 of entropy is 0. But this is for aqueous solutions. When we have aqueous solutions, we're going to have this scenario pop up. Because that aqueous solution is going to consist of ions. And so it's going to be 1 mole of HCl, in this case aqueous, times minus 136.4 joules per mole Kelvin. That would be the units there. All right, I only have one product here. How much of this entropy is due to H plus? How much is due to Cl minus? And that's arbitrary. 0 to H plus, all due to Cl minus, we saw earlier. All right, minus, now we have half a mole of H2. And so half a mole of H2 gas. Let's take a look. Oh, what am I doing?
Okay, I was like, why are we using that value?
Yeah.
I was just going to ask you that.
Okay.
I'm very confused. I'm so confused, but this makes it.
Because I'm reading the wrong paper, sorry. Okay, this is correct.
That's correct.
This is correct. This is not, this is the, this is something else.
Do we need to worry about that last?
No, we don't. We aren't going to do anything with this last one. Okay. This one is this heat capacity, CP. This one is the entropy. Entropy.
So we're supposed to be using the S.
Yes, we're supposed to be using the S. So I screwed that up. Let me back up here. Not the heat capacity. We're not supposed to be using the heat capacity. And the heat capacity is going to be funny because of that. But the entropy should be here. And so the entropy of the HCl aqueous here is 56.5. And so let me back up. How much of this is due to Cl minus? How much is due to H plus? And so it's 56.5. How much is due to H plus? 0. How much is due to Cl minus? Yeah, so you know. That's what I meant. Okay, sorry for the confusion. So the 1 mole of HCl aqueous is going to have 56.5 joules per mole Kelvin. Joules per mole Kelvin. Okay, then we're going to go to H2. H2 is a gas. This entropy is kind of low, isn't it? This one we don't have to worry because in this one, you know, when we do this, when we look at the entropy of H plus, the entropy is all going to be shifted to the low side because, you know, this is 0. It's actually a lot higher. So all the entropies are shifted to the low side. And then Cl minus, all the entropies are shifted to the high side because Cl minus doesn't have all the entropy. It's shared, right? And so we have a systematic error that pulls it to the left, and a systematic error that pulls it to the right. So when we combine them, the systematic error cancels. And therefore, this is an accurate number here. Does that make sense? Somewhat? So in other words, the error cancels out. And so if we form both the cation and the ion, this should be okay. And the reason this is so low is because of this hydrated or solvated ions. You know, they're going to form what we call spheres, hydration spheres, and those are pretty well ordered. But anyway, we're going to go back to 1/2 mole of hydrogen. A full mole of hydrogen is going to have an entropy of 130.7, which is still fairly low, but hydrogen is not a complex molecule. It's a pretty simple molecule. So this is lower than our typical gases, which would be like over 300. And so this is fairly low. 130.7 joules per mole Kelvin, plus 1/2 mole of O2. And the entropy for the O2,
CO2.
Cl2 is 223.1. Cl2 is 223.1 joules per mole Kelvin. All right, so let's go ahead and calculate the entropy change here. I got an entropy change of minus 120 joules per Kelvin. Is that what you guys get? And so we went down in entropy. And it makes sense because we have these gases. Gases have high entropy. Aqueous solution is going to have lower entropy. And so we dropped in entropy here. Is that favorable? No, because in nature, we want to not decrease entropy, we want to increase entropy. But when we think about this, if I have a mixture of hydrogen and chlorine, is that a reactive mixture? Hydrogen and chlorine is a very reactive mixture. You know, normally when we think about it, what do you think is the stronger oxidizer in general? Chlorine gas or oxygen gas? Oxygen gas, do you think, is a stronger oxidizer? Well, what does the redox say? In other words, if you inhale a lungful of chlorine gas versus inhaling a lungful of oxygen gas, chlorine gas seems to be worse, doesn't it? Yeah, I would think chlorine gas is a little stronger of an oxidizer, although oxygen is pretty good. And so, in a reaction like this, again, hydrogen with oxygen is an explosive mixture. So hydrogen with chlorine should at least be an explosive mixture. And so this reaction is very favorable. This reaction has a driving force. We're going from a stronger reducer and a stronger oxidizer to a weaker reducer. Chloride is a much weaker reducer than hydrogen. And H plus is a much weaker oxidizer than chlorine. So stronger to weaker. And so this reaction has plenty of driving force, but the driving force isn't coming from entropy. Entropy is not favorable here, so the driving force must be coming from energy. Energy. So how do we weigh these things out? Well, one way we weigh these things out are energies are typically in kilojoules per mole, but when we look at the entropy is just in joules. But there's more to it than just weighing joules versus kilojoules and seeing how they weigh out. You know, we see this is delta H is going to have a significant. So the situation comes up now. How do we use this? So I just calculated entropy for this. Now, how do I use it? Now, that's going to bring us to, well, how we're going to use this is we're going to use this using the second law of thermodynamics. What we want to do is we want to quantitate the driving force. So we have this relationship, energy and entropy. But the second law is going to allow us to calculate the driving force for reactions. And the second law just says this: for spontaneous processes, delta S of the universe is greater than zero. And so what that just says is that if we want to figure out if the reaction is going to be spontaneous or not, we have to just calculate delta S of the universe, and then we can figure it out. But we just calculate delta S of the system here. Our system is just this reaction here. Then we have to calculate delta S of the surroundings. But is calculating delta S of the surroundings even feasible? No, it's not even feasible. So, you know, this is what's observed empirically. You know, it's observed that for every spontaneous process, the entropy of the universe increases. If the entropy of the universe is equal to 0 or less than 0, then it's non-spontaneous. So this is not practical. We can't use this. But, you know, we have some relationships that we can do for this. And that is, the first thing we can do is we can say that delta S of the universe consists of delta S of the system plus delta S of the surroundings. Now, there's a relationship between the the heat, we were talking about that, like water has a very high heat capacity, It's got a lot of ways that it can absorb energy. And so there is a relationship between delta S and heat, which we'll talk about here. And we can quantitate that relationship between delta S and heat. So let's take a look. At this here. And 13.2, D is just a very, very small delta. And so you can think of this as delta S, where the change is, D is like what we call infinitesimally small delta. Is equal to dq, which is delta q, reversible over t. And so what we're going to just say is, well, delta q is just the heat that's exchanged. And so I'm going to simplify that, and I'm going to use that for the surroundings here. So delta S of the universe is equal to delta S of the system. Delta S of the system is pretty easy. We just calculated delta S of the system for that reaction. So we just used appendix D to figure it out. But this delta S of the universe is complicated. And so rather than saying delta S of the universe, what we're going to do is we're just going to call that Q over T. We're going to call this Q reversible of the surroundings. Reversible has a specific meaning. And if you do something reversible, you have to do these in infinitesimally small steps that can be easily reversed, like equilibrium. Equilibrium goes both ways, and forward and backwards. And so there's that constraint to that. Okay, and then we get the Q reversible over T. And then what we can do is we can use the first law of thermodynamics, because any heat that's absorbed or emitted by the surroundings has to be emitted or absorbed by the system. The heat can't just disappear. And so any heat of the surroundings would be the opposite in sign of the system. That's the first law of thermodynamics. So what we're going to do is we're going to use the first law here. We're going to say delta S of the system plus a minus Q reversible of the system. Well, we know it's got to be reversible, so I'm going to drop the reversible and keep that in the back of the mind that there's other constraints to this. And then we do this. We do the definition of enthalpy. You know the definition of enthalpy? What is the enthalpy, or how was enthalpy defined? Enthalpy was defined using delta U. Delta U is equal to Q plus W. Any change in internal energy is going to be manifested in heat exchange between the system and surroundings, and work exchange between the system and surroundings. And that means that the heat is equal to delta U minus W. But do you guys remember state functions? Kind of. Heat is not a state function. The amount of heat you get is not always the same, because state function would always be the same. You always end up with the same. Like delta U is a state function, delta H is a state function, but heat and work aren't. So if you have a battery, are you always going to get the same amount of heat from that battery? Every time you use a AA battery, do you get the same amount of heat? No, it depends. I mean, what do you put that battery in? How efficient is that? How much heat is going to be dissipated? Are you always going to get this exact same amount of work? If you could always get the exact same amount of work and the exact same amount of heat from a AA battery, then we call that a state function, because we're always going to get the same heat and work. But we don't. We can make it a state function. You know how you can make the battery give you the same amount of heat each time? You make it do the exact same amount of work. If you make it do the exact same amount of work, and let's say they build the batteries with precision and accuracy, that we always have the same amount of material, then if we always do the same amount of work, then we're always going to get the same amount of heat. That's how you make it a state function. You know, it's like the walk. Like, how much energy does it take to walk? Well, if you always walk the same path, then it should take the same energy. But the problem is you don't always have to walk the same path. You could walk different paths. And so that's going to give you different amounts of energy. And so what we're going to do is we're going to put two restrictions on this. We're going to keep the work at constant pressure and P delta B work only. P delta B work is the natural work of the chemical reaction. And so if we always do the same amount of work, we're always going to get the same amount of heat. And therefore, Q, rather than calling it Q, which normally isn't a state function, we can have different amounts of heat, we call Q a new state function. The new state function is delta H. So Q is defined as delta H here, which is equal to delta U minus the work, which would be a minus P delta V. In other words, delta U plus P delta V. So this is the equation from chapter 7 that we have. So this is the definition. So all we have to do is the same thing here. Oh, okay, so we just have to measure the heat of the system. Measuring the heat of the system is easy. We could do that using calorimetry. Okay? And so what we'll do is we'll restrict this. We're going to restrict this to constant pressure and P delta V work. And if that's the case, then delta S of the system is going to be plus a minus delta H of the system. And so rather than using Q, we can use our new state function, delta H. Well, it's not new, it's chapter 7. It's old by now, but okay, and then what we're going to do is we're going to do this. We're going to multiply both sides by minus T. If we multiply both sides by minus T, we get minus T delta S of the universe. Minus T delta S of the universe is going to equal, actually, do I want to do minus T? I'm going to rearrange that. I'm going to call it delta H of the system plus T delta S of the system. Now, a state function, you always get the same amount. And so, so temperature is a state function. You know, if we think about delta T, you know, let's say the temperature changed from 5 to 10 degrees C. It doesn't matter what path you take. You could go from 5 to 1,000 and drop back down to 10. The delta T is always going to be the same. And so this is a state function. Delta S of the universe is a state function. This is a state function. And this is a state function. And therefore, these are all state functions. So just like we did for delta H, we're going to define a new state function. And the new state function is going to be this. It's going to be minus T delta S of the universe is going to be defined as a new state function called the Gibbs free energy, delta G. And delta G is going to equal delta H. This is delta G of the system. Is going to equal delta H of the system plus T delta S of the system. And what we want for delta G are Gibbs free energy. This is the change in the Gibbs free energy. Gibbs is a famous thermodynamicist. For delta G, we need the entropy of the universe to increase. So if the entropy of the universe increases, that's positive, times the negative T is going to give us negative. So what we need here is we need the delta G to be more negative. That is, we want this to be less than 0 to be spontaneous. If delta G is less than 0, then delta S is greater than 0, which means the entropy of the universe is increasing. That would be spontaneous. So, can we determine delta H? Yeah, we can determine delta H. We can determine delta S. It's not a problem. So here is our energy, and here is our entropy. Terms. And the energy term we can calculate just using techniques from chapter 7, and the entropy we can calculate using techniques from chapter 13. And so turns out to be straightforward. If we want to figure out the driving force, we're going to have a driving force if delta G is less than 0. And so this is our second law of thermodynamics. Now, the second law can be stated in different ways. One is delta S of the universe increases. But, what is energy and what does that have to do with entropy? Well, actually, they're both related. This delta S of the system is positional energy. Positional entropy. Delta H of the system is actually related to entropy. And delta H of the system is heat. Here we call heat. Heat of reaction. And so this is related to energy entropy. Again, this is positional entropy here. What is energy entropy? Energy entropy is like this. Let's take methane plus 2 O2s at 298 Kelvin. We say that this has fairly high chemical potential energy. And then we drop it to CO2 plus 2H2O liquid at 298 Kelvin. This has lower chemical potential energy. And so there was a change in energy here. This change in energy, we're going to do this under constant pressure and PV work only. So we're going to use delta H to indicate what the change in energy is. And that change is going to factor in the work done on or by the system on the surroundings. And so we're going to have delta H here. And this is delta H is less than 0. That means heat is lost, right? Is Q. Q is lost, heat is lost. And so basically, this is what happened to the energy. What happened to the energy? What happened to the energy is nothing happened to the kinetic energy. What happened to the potential energy? Now, the potential energy here was high, and then we went low, so we lost potential energy. Where did the energy go? That energy, the potential energy, was converted into heat, which is kinetic energy for the surroundings. So in terms of entropy, which has higher entropy? Kinetic energy, heat, or potential energy, the bonds? Which one's more ordered, would you say? Potential energy and wrapped up in the bonds, or kinetic energy, as in heat? Potential energy is more ordered. And so what's happening is we're increasing entropy because we're converting potential energy into kinetic energy. Kinetic energy is a more disordered form of energy. You can't do as much can you do as much work with heat as you can do with a combustion reaction like this? Combustion reaction, we can power a car, right? And so if you put methane, these are these CNG, compressed natural gas vehicles driving around. I think I saw like Amazon having these. So you could do that work driving the car, but could you fill up your tank with heat? I'm going to make my car hot. I'm going to make my car really hot. Are you going to drive around much with a hot car? No. No, and so it's a more disordered form of energy, and we can't do as much work with that as we could with potential energy. We can get a lot of work done from this. The same thing with battery. If you take all the energy of a battery and just discharge it as heat, are you going to be able to do much work with that heat? No. No. But if you have the battery and power a motor, then you can do work. But you can't take that heat and power a motor, are you? No. And so this is, so we have two types of entropy. And so this is the entropy of the universe is increasing, but the entropy of the universe is tricky because they're going to divide the entropy of the universe into the entropy for positional entropy and the entropy for energy entropy, which is going to be given by heat that's going to be given off by the reaction.
So like solar panels, do those take, would you say those take heat?
No, it's not heat. Those take light.
Oh, it's light.
Yeah.
Okay.
And then they promote electrons, and so they do work. It's taking that. It's not heat.
Do we have any?
There are things that they are using to convert heat into electricity, but the efficiency of that's very low. But still, why not? Thermoelectric generators, something like that. There was an article about that recently in C&E News. I don't know if they call it thermoelectric. Thermoelectric. I mean, they're becoming more efficient. Thermoelectric generators. They're becoming more efficient, but 100 watt. 100 watt, you could power a light bulb or light bulbs. There was a recent article on this. There's thermoelectric, there's piezoelectric. Have you heard of piezoelectric, which can convert mechanical work into electricity? So people are thinking about putting piezoelectric materials in their clothing so that when they're moving, they can generate electricity that way.
Is that what do you call them? The windmills? Or is that?
When the windmills are powering a generator, it's like electric motor. And so piezoelectric is just movement. Thermoelectric, so you can read about this, but the problem is converting heat into electricity is very inefficient. Piezoelectrics, I'm not sure what the efficiency of those are, but apparently they're pretty decent because some of the piezoelectric clothing that they're looking at can recharge phones and that kind of stuff. Piezo, and I was looking at some of the clothing. I don't know if it's comfortable to wear or if it's not. Piezoelectric clothing. If it's going to be very stiff. I imagine it's not going to be so flexible. So here's some a research team at Chalmers University of Technology in collaboration with Swedish School of Textiles has invented an energy generating fabric that's flexible and works more efficiently when more weight is placed on it or when it's wet. And so, anyway, using heat, so if we convert this into heat, then using that heat is difficult because of its higher entropy. However, delta H doesn't have to be converted into heat. Delta H can be converted into work. Just because delta H is equal to Q, it doesn't have to all be dumped as heat. And so what we can do is we can convert a lot of this delta H directly into work rather than into heat and then work. Does that make sense? And that's what we do in a compressed natural gas vehicle, where rather than converting it all into heat, we're converting some of that, which would have gone into heat, into work, which would be much more efficient than doing this. Okay, so this is the main calculation we're going to do in this chapter. You know, what we want to do is we want to figure out what delta G is. And so most of our calculations in this chapter are going to be involving delta G. Now, we're going to have two delta G's that we're going to look at. We're going to look at delta G under standard conditions. And so if we have delta G under standard conditions, then we'll need delta H under standard conditions minus T delta S under standard conditions. And then we're going to do delta G under non-standard conditions. Well, there's a problem now. The problem is this. If I do delta G under non-standard conditions, then I need delta H under non-standard conditions. But I don't have delta H under non-standard conditions because I have a table full of values of delta H under standard conditions. So now basically these two aren't equal. Delta G under non-standard conditions is not equal to delta G under standard conditions when we change those conditions. And delta G under non-standard conditions is going to equal delta H under non-standard conditions minus T delta S under non-standard conditions. But what we're going to say here is that delta H under standard and delta H under non-standard are kind of close enough. And then delta S under standard conditions and delta S under non-standard conditions are somewhat close. And so that will give us some, but the temperature is also going to play an important factor in this as well. The other way we can do this is we can correct it. And so, or what we can do is we can use some thermodynamic equations, and I'm not going to get into the derivations of this, but delta G under non-standard conditions is equal to delta G under standard conditions plus a correction factor. And the correction factor is going to be RT ln of Q, where Q is the reaction quotient. And so it depends. The familiar reaction quotient, which is just the product of the reactants. So we're going to be paying attention. Are we under standard conditions, non-standard? What is the temperature? All these things are going to be important when we're calculating delta G. So we're going to spend our time calculating delta G. And so let's take a look at some problems here from this. And so we'll zip through. There's some more relationships which we'll talk about. And shortly. Thermodynamic relationships, equations. And let's take a look at some of these. What happened to the entropy here? CCl4 liquid goes to CCl4 gas. Entropy increase. What happened to the energy? In order to go from liquid to gas, you have to add energy. So this is endothermic. Well, it's endothermic. Is that favorable or not favorable? Endothermic is delta H is positive. What do we want for delta G? We want delta G to be negative. So that's not favorable. However, delta S increases. That is favorable. And so delta S increases, that's favorable. But what temperature are we doing this at? And then we can see, is that going to be spontaneous? Right now, I don't know if it's going to be spontaneous or non-spontaneous. Will this be spontaneous or not? And so let's see if we have the data to do a quick calculation for this. So the data is going to be back in Appendix D. And we're looking for CCl4. Organic substances have the data here in this. This is a separate table. for a lot of the organics that we deal with. And do we have that? No, we don't have that. So we aren't going to do this calculation, unfortunately. It would be an interesting calculation to see. And so all we can say is, well, it depends. It depends on what the temperature is, and it depends on how big delta S is. You know, delta S is favorable. Can delta S be big enough so that T delta S cancels out the positive delta H here and makes this whole thing negative? And so if minus T delta S is bigger than this, then it's going to be favorable. Okay, so we have a name for that. And so this is all we can say here. For this particular reaction, 13, let me go back to that here. For this particular reaction, this is what we can say. Since we aren't going to be able to calculate it, and we don't know what the numbers are. And so when we have CCl4 liquid goes to CCl4 gas, what we say is that this is favorable, i.e. has a driving force at high temperature. What is high temperature? I don't know what high temperature is. It's just a temperature that's big enough to make that delta S overpower the delta H. That is. In other words, delta H is unfavorable, but delta S is favorable. And so if we can make this delta S term big enough that it cancels out this term, then it's favorable. We can do that by increasing the temperatures to some point where the T delta S is bigger than the delta H. Does that make sense?
It means high temperature, right? At high temperature.
Favorable at high temperatures, temps. Let's say at high temps. High temps could mean below room temperature. You know, I don't know what it means. In fact, CCl4, if we had the data, we could calculate it, what that temperature is. In fact, this is what we call boiling. And so there's one more thermodynamic equation that we can come up with. And so if this is boiling, then what we have here is that we're going to have an equilibrium between liquid and gas. If we have an equilibrium between liquid and gas, then what we see is that delta G at boiling is equal to 0, which is equal to delta H minus T delta S. And so temperature is equal to delta H over delta S. This is going to be the boiling point. But we need the delta H at the boiling point and delta S at the boiling point. So we could do this. Let's do this calculation for something that we have data for. And so we'll look at something similar to this problem, but we're going to look at H2O liquid goes to H2O gas. Yeah. So let me write down over here. Delta G less than 0 means it's spontaneous. Delta G equal to 0 means it's at equilibrium. Delta G greater than 0 means it's non-spontaneous. And so this is the at equilibrium point. You know, when we have boiling, we have an equilibrium between the liquid and gas phase. And so that's why I said the delta G is 0 here. All right, let's take a look at a specific example of something very similar to this that we know what the answer is. And that's going to be water. And so let's figure out what delta H is, delta S is, delta G is for H2O liquid going to H2O gas. So we have to go to oxygen here in our data table. Or hydrogen. Go to hydrogen. And so we see H2O liquid goes to H2O gas. So first let's calculate delta H. Delta H will be delta H formation of the products, H2O gas minus, so that's minus 241.8. Minus delta H formation of the reactant. So this is going to be a minus H2O liquid is minus 285.8. It's 285.8. The units for this will be in kilojoules per mole. Well, actually, it's just, we're dealing with 1 mole, so it's just kilojoules. And this is going to be 44.0 positive kilojoules. It's 44.0 kilojoules. Okay, let's calculate delta S. Delta S, the products, H2O gas should have a higher entropy, 188.8 and 69.91. 188.8 minus 69.1. Now the units for this are going to be joules, 69.91. Joules per Kelvin. Moles cancel because I'm just dealing with 1 mole. And so what is this going to be here? So 188.8 minus 69.91 equals 118.89. 118.89. We're only allowed 1 decimal place. That's so stupid. Joules per Kelvin. All right, so let's go ahead and calculate delta G. So if we calculate delta G is equal to delta H minus T delta F. Delta H is 44.0 kilojoules. T is, what temperature do you want to do this at? Well, there's only one temperature we officially should do this at, and that's 298, because that's what the data is. This is delta H 298. This is T is at 298, and delta S is at 298 Kelvin. That's where we get in the data table. So this is 298 Kelvin. I'm only going to go to 3 sig figs here, times 118.89 joules per Kelvin. Kelvin cancels, that leaves us with joules. So I'm going to have 44.0 kilojoules minus, okay, this is going to be 298 times 118.89. This is going to give us 35,429 joules. But there's a mismatch in units here. So what I'm going to do is I'm going to convert kilojoules into joules or joules into kilojoules. Let's go ahead and convert this into kilojoules. So 1 kilojoule is equivalent to 1,000 joules. So I'm going to have 44.0 kilojoules minus 35.429 kilojoules. Was it enough? Was entropy enough? Entropy is favorable. This is unfavorable. Entropy was favorable. Did entropy win or did enthalpy win? Well, we can see. What does this come out to? 44 minus 35.429. What did you get?
8.5.
8.5?
7.1.
7.1. 2-1. Enthalpy 1. Enthalpy 1. So what this means is water does not spontaneously boil at 298 Kelvin. And so we say that this is non-spontaneous. But, you know, entropy is favorable. And so if entropy is favorable, all we have to do is increase the temperature and make that term bigger, and eventually it'll cancel out the enthalpy.
That's just saying if you increase the temperature. When you just increase the temperature, then it would become spontaneous.
Yeah, let's take a look here. At what temperature will this become spontaneous? Would be the question. At what temp will this become spontaneous? Now, when I'm asking that become spontaneous, that is, I want the delta G to transition from positive to 0 to negative. And so this is the transition point. When delta G is equal to 0, it's going to transition from positive to negative. And so what I'm going to do is I'm going to set my delta G to 0. Well, it's going to be set to 0 anyway, because this is, when it's boiling, it's at equilibrium. So delta G is equal to 0, which is equal to delta H minus T delta S. And so T is going to equal delta H over delta S. Delta H is 44.0 kilojoules. Delta S in kilojoules is going to be 35.429 kilojoules per Kelvin. And so what does that come out to? So let's take a look. It's going to be 44 divided by 35.429. Oops, I did it backwards. I did it right. Oh, I made a mistake, sorry. This is delta S, not T delta S. Delta S was point, I'm going to convert it to kilojoules, 0.11889 kilojoules per Kelvin. So let me redo that. So it's going to be 44 divided by 0.11889. And so I'm going to get 370.09 Kelvin. What's the boiling point of water? 373 Kelvin. We're off. It should have come out to 373 Kelvin, right? But then we did something. We did this. Right, we weren't using the correct delta H and delta S. The temperature should equal the delta H at the boiling point over delta S at the boiling point. What we did was, rather than using that, we're just going to say it's approximately equal to delta H at 298 and delta S at 298. So we weren't using the proper delta H and delta S, but we don't know what the proper delta H and delta S is because we don't have the temperature. And so this calculation is going to be in error because we aren't using the right delta H and delta S. But that's acceptable because there's no other way we can get this. And so this is our estimate of the boiling point here. Does that make sense for that? And so we got to be thinking about these things all the time. Are we doing it under standard conditions, non-standard? This is under standard conditions. If we go non-standard conditions, what happens to the boiling point? So is this going to be the boiling point on top of Mount Everest? Yeah, this is going to be at the boiling point at sea level, which is close to 1 bar. But if we're on top of Everest, it's 1/3 of a bar. And if we're at 1/3 of a bar, that's non-standard conditions. So how can I calculate? Or if I have a pressure cooker, that operates, let's say, at 1.5 bar, is that going to be the boiling point in the pressure cooker? No. So I need to do things under non-standard conditions as well, because I'm not always at 1 bar of pressure. And so if I want to do this under non-standard conditions, then how do I do this? Well, this will be the boiling point at 1 bar and not at 298. Remember, there's no standard temperature. This would be at 1 bar. 1 bar is standard conditions. What about the boiling point at non-standard conditions? Is there a way to make water boil at room temperature? Yeah, there is a way to make water boil at room temperature. Now, that would be under non-standard conditions. So an example of this is, let's boil water. Well, let's do two calculations. One, we'll just say, what would you predict the boiling point to be, at the summit of Everest? Boil water at 1/3 of a bar. Let's figure out what the boiling point would be there. Well, that's non-standard. If it's non-standard, then we have to deal with delta G non-standard. Delta G non-standard is equal delta H non-standard minus T delta S non-standard. And I don't have the delta H. Can I use the delta H under non-standard? I made an error earlier because really, if I have delta H under non-standard, it is not going to equal delta H under standard. And it could be quite different. The same thing with delta S under non-standard is not equal to delta S under standard conditions. What I did here was something a little bit different. Here. This one we could say, and I should have done that earlier, but delta H under standard conditions at some temperature T, we're going to say is going to be close to delta H under standard conditions at 298. This one's okay. And delta S at some temperature T is going to be close to delta S under standard conditions at some temperature, not some temperature, but 298 Kelvin. However, delta G at temperature T is not going to be equal to delta G at 298 Kelvin because delta G changes dramatically with temperature. As we see, you can convert things from spontaneous to non-spontaneous just based on the temperature alone. And so we need to keep these things in mind here. This becomes more trickier to assess, but these ones are fairly okay. For sure, the delta G changes a lot with temperature, as you can see here, because that could change the whole weighing of these two terms, and it can reverse the spontaneity of a reaction or vice versa. So what are we going to do for this? Well, what we're going to do is we're not going to put any values in here. What we're going to do is we're going to determine the delta G under standard conditions and then correct the delta G under standard conditions with this, which is equal to RT ln a Q. And then that correction, where does that correction come from? That correction comes from working with thermodynamics, and we aren't going to get into it. We're just going to use the equation to do our calculations. So delta G under standard conditions is not a problem. It was 8.5, it was plus 8.5 kilojoules, 8.5 something kilojoules. R is not a problem. R is 8.3145 joules per mole Kelvin or joules per Kelvin. T is the temperature. We're going to try to boil water at 1/3 of an atmosphere. So T is the temperature we're trying to figure out. And then L and a Q. What is Q? Well, Q is, okay, we're going from H2O liquid to H2O gas. And this is QEQ, which is related to KEQ, the thermodynamic equilibrium constant. And so if I have a gas, it could either be QC or QP. When we're doing it thermodynamic, for gases, we pick QP. So this one's going to equal QP, which is going to equal the partial pressure of the product. So this will be the partial pressure of H2O gas over the partial pressure of the reactants. Well, H2O is a pure liquid, and so that just gets activity 1. And so it's just the partial pressure of H2O gas. Well, in order for boiling to occur, the partial pressure of H2O gas has to match the atmospheric pressure. When the partial pressure of liquid, the vapor pressure that is, matches the atmospheric pressure, we have boiling occur. And so Q in this case is just 1/3 of a bar. And then we just plug it in. But I'm way over time, so sorry. Let me stop here, and we'll finish this calculation next time.